All right, so now I want to go through a recovery using a test image from a DFR test image. These are hosted at cfreds-archive.nist.gov. There are several images out here, and these are specifically for deleted file recovery. They come in different formats. So the one that we're going to do right now is recovering a file with 2 fragments, just because I wanted to demonstrate how to recover a file which is spread across separate sectors and just kind of see what it looks like. You can download all sorts of different formats, just depending upon if you want to try different tools or do different things. And there's many different versions. Nice thing about this is they go through their image layout documentation, which is a large PDF which lists all sorts of information about every single image, how it was created, what they did to create it, everything else. So definitely recommend checking out the deleted file recovery site and then playing around with some of those. So to begin with, we'll need to get the file onto our Kali system. And we can do that through a virtual or through a shared folder. So if you just go to Devices, Shared Folder Settings, create a new shared folder, I can go ahead and select the path for where I have the files. So I created a folder down here, and I'm just going to select this, select folder, read only, auto mount, make permanent, hit OK, and then yes, and that will automatically mount it, and it should stay mounted. So now if I look under Media, SF, that folder, I'll see everything there. Now I've already downloaded these and put these under Images. So if I look under Images, Examples, I will see the DFR02 FAT DDBZ2. This is a bzipped compressed image, so I'm going to go ahead and copy that locally. Place it right here, and now I will see this file right there. So I'm going to go ahead and unzip this. So it's bunzip 2 DFR, that, and it takes a second. It depends upon the particular image size. Usually it doesn't take too terribly long, but it's just extracting that and then leaving behind the original file. So now we can see we have this image here, and if I look at this, I can see that this is taking up, what is that, 1 megabyte in size. And there's the image. So now we're going to look at this image and do a little bit of analysis on it. So first, I'm going to look and see what partitions does it actually have. So this MMLS will list the drive partitions, and we can see that the beginning has a partition table. There's an unallocated space here, and this is giving you the size of all of it. Now, all of these, they're 512 byte sectors. So the partition table on this takes up 1 sector, so 512 bytes. There's 128 sectors which are unallocated. And then we have a FAT12, FAT16, and a FAT32 partition. And then finally, there's some unallocated space there. All these DFR images, all the FAT images, they all have 3 separate FAT partitions, and it's designed to test different file recovery tools on the different FAT partitions. For our purposes, doesn't matter if we use the FAT12, 16, or 32, because it's going to be exactly the same. So I'm just going to go ahead and choose the FAT16. So looking at this, that is going to be partition, or that's going to be entry number 3. It's going to start at sector 16512 and end at sector 82047, has a total length of 65,536 sectors. And we can go ahead and start to explore this a little bit. So we can look at the inodes. So there's a command called ILS, and this will list the inodes. And again, FAT doesn't have inodes so much, but it will be a index identifier for it. So we can say ILS -O, and this is the offset for that particular sector. So we're looking at this sector, so 16512. And we need to give it the file that we actually want to analyze. So dfr 02-fat.dd. And this will list the inodes for the deleted files. Now, this won't list everything. If you want to list everything, there's a -e, which will list deleted and not deleted. So we can just pass that in there. And this will list every object in there. Now, doesn't really help to see all of that because, well, those are just inodes. So maybe we want to see the actual files. So there is a command called fls, which will display the file information. So the command is very similar to ILS, fls-o, and then the offset, which is 16512, and then the file. And we can see all of this information here. So this is our volume label entry. This is one of the files which exists on the file system. This is one of the files which has been deleted. So the star there is the deleted flag that this FLS command or the sleuthkit adds in there. There's two other valid files, and then there will also be the MBR, the FAT tables, and then orphan files location. We can add a -r there that will show us the same information. The difference with the -r is we'll recurse on directory entries. We don't have any directories in here, so we can't really recurse on those, so there's not much of a point for that. But the key thing is this is our deleted file, which if we look back up here, when we ran ILS on this, notice that the only entry that it showed was inode 8, which had been freed. And that's what that F means. A means it's allocated, F means that it's freed. There's other information in here. There's the UID and GID. FAT systems don't have a user and group ID, so that's going to be more used for NTFS or ext4. There's the modified time, the access time, the create time, or the, I believe that's the creation time there. This is the compressed time, I think. I don't remember exactly which one that is. We'll have to check the documentations. Modes, which in this case, that's 777. Again, FAT so file systems don't have really any security, so you aren't going to have any other modes. NTFS and ext4 will have different file system permission modes. There's also links, and then there's the file size or the size of that particular object. So notice that when looking at these, there's 5, 10, and 12, which are not deleted. Those are 2 kilobytes in size. The one which was deleted is 4 kilobytes in size, and they did that so that it could actually spread across 2 different sector chains. So if we want to look at this a little bit more, we can go ahead and look at something like hexdump. And we can look at the beginning of this particular file system. So I can go ahead and do that. And this is the beginning of the file system. This is going to be the hex values of all of it. So not really that useful, but we can look at where these files are, and specifically where this is, because that will have the entries for these files. So in order to do that, we need to do a little bit of math. So MMLS. So our starting point is there. And so let me go ahead and bring up the calculator. So if we take 16512 times 512, that is 8,000, 8 million, 8 megabytes in, basically. So hexdump has a couple of flags. There's a -n and -s. And so -n is a number of bytes to display, and -s is a number of bytes to skip. So we want to skip past all the beginning here and get to the beginning part here. So in this case, we want to see 8454144. And let's go ahead and display just a single sector's worth of bytes, or yeah, single sector worth of bytes. And so now we can see that this is the beginning of our FAT16 file system. That's going to be the beginning mark of it, and this will be all sorts of information. When we're looking at this, we want to see, okay, so where does this file actually start? Where does this actually end? Where are the sectors kind of displayed? So there is a command called fsstat -o, and again, we'll give it this same offset, 16512 DFR, and this will show us information about our particular file system. So notice that, hey, this is an MS-DOS 5.0. Hey, there's the OEM MS-DOS 5.0. There's going to be the rest of the information which is in here. This is all calculated based off of what it sees, but the metadata information goes from 2 up to that number. The root directory exists at entry 2, not at entry 1. And this is the file content. So these are the files that exist, and these are the sectors that they span. So this file here occupies 4 sectors, which makes sense because it's a 2 kilobyte file. It starts at sector 298, ends at sector 301, and that's the end of file. This file starts at sector 306, occupies 4 sectors, ends at sector 309, and this file starts at sector 314 and goes to 317. So if we want to see a little bit more of the information, we can go ahead and use istat, and then the offset, DFR, and then we can give it one of the inodes that is in there. So we can go ahead and say 5, for instance. This is that particular file, alcor.txt. It has its file times, written, accessed, and created, and the sectors that it spans. Notice that that matches up with those there. It's a file, archive, so on and so forth. If we give it the deleted file, which is, I believe it was 8. Yes, 8. We'll have that same information, but notice that the first letter of that particular file is an underscore. That's what the sleuthkit uses to represent E5 or hex E5. It has the similar information there. Notice this created is going to be a little bit, or sorry, the written is going to be different. That's when the file was deleted. And these are the sectors it spans. It's spanning 8 sectors, which makes sense because it's a 4 kilobyte file. And there is a gap between the sectors. So really this file exists in between there and in between there. So that's why it's a fragmented file. So we can't just say grab all the blocks across a specific span and that's the entire file. We have to look across multiple spans. So getting back to hexdump, just because we want to see where that file actually exists, we can look at this. We can see that the starting point is sector 302. And really what we care about is the beginning part there. So we want, okay, so if we want to actually see what it looks like on the file system, we need to look at the data area, specifically because this is all inside of the root. We want to begin at the root directory. And so we can use hexdump, and as long as we calculate what the offsets are for that, we can easily start to see where it goes. So to begin with, we need to do a hexdump -c DFR and then -n-s, and I'm going to go ahead and do a head there just in case. We need to look at what this root directory looks like. So to calculate that, we want to go ahead and take, let's see how big it is, 295 minus 264, so it's 31 sectors in size. So that times 512 means that we need to look at 15 kilobytes worth of space. 872. And our start point is going to be at sector 264. Now, that 264 is going to be offset by the beginning sector for this. And I cleared the window, so if I open up a new window and I do an MMLS, DFR, DFS, oh wait, I'm under desktop. So our starting sector is 16,512. We need to add 264 to that, so 16,512 plus 264. So we need to start at that sector. Each sector is 512 bytes in size, so our starting point is 8589312. And so if I run this, this is the beginning of that particular directory. Notice that we see our file name there. And in fact, I'm going to get rid of this head. And we can see everything here. So we can see the files that we had on our particular file system. So there is Alcor, there is Capella, there is Deneb, and then here is Beetlejuice. Now, if you're unfamiliar with it, this tilde1, FAT16, FAT12, had a 8.3 file naming scheme. So there were ways that you could get larger file names, but it had to be stored as a 8.3 file name for that. So this is the file name, this is the extension. And you'll notice that the first character of this particular file name is hex E5 to indicate that it has been deleted. So this is our deleted file, and this contains all the information as to where the file exists and where it actually starts. So that shows us the information for our file. So now let's go ahead and go into recovery. So let me pull up the iStat again for our particular file, which is entry 8. And this is our file that we want to recover. Now, the Sleuthkit has a nice tool known as iCat that you can just say, all right, we want to start at 16,512 on DFR, and we want to recover 8, and I want to write it out to beetlejuice.txt. And you'll notice that there is a new file here, and I can go ahead and cat that particular file, and this is the recovered file. So you'll notice that this is what the site had done when they created the file. Is there's the beginning of the file, this is in segment 1, those are the blocks which contain segment 1, starting with block 4, this is now in segment 2, which spans those particular blocks there. And that's going to be all 8 blocks for that file. So that's really how hard it is to recover a file, assuming that everything happens nicely and it still exists, it can follow those sectors, and it can recover it that way. Now, I want to show you a different way to recover the file, which is using DD. So we're going to go ahead and look at that file again. So it's going to be iStat, that, and these are the sectors that the file exists in. And we're going to use a utility called DD. Now, a lot of you have heard of DD before. It's also known as Data Destroyer, because if you do this wrong, you can easily start to wipe out data. We'll just make sure we don't do it wrong. So I'm going to go ahead and create a temp folder. And I'm going to DD, and I need to give it our input file. Since I'm in my temp folder, I need to go up and pass in that. And I'm going to give it our output file, and I'm going to just say this will be text1.txt, and this will be text1.txt, and I'm going to give it a block size of 512. I'm going to give it a count, and we're going to go across 4 blocks there, and I'm going to tell it to skip the first. How many blocks do we actually need? Well, that is our starting point, plus, and we want to start at sector 302. So we want to skip the first 16,814 blocks. Okay, so that wrote out 2 kilobytes worth of data, which is what we expected. And if I cat text1, notice that I have the beginning parts of that particular file. Now I just need to do the same thing for the second file. Now I'm going to write it out to a different file this time. Count's going to be the same, and I'm going to skip, and so I need to, let's see, so it's going to be, what is that, 16,000 plus 310. So I'm going to skip 16,822, write that out to text2. Now I have those two files, and now I'm going to combine those files together and output this to Beetle. I'm misspelling Beetlejuice for some reason. Okay. And now I have my output file right here. And now I can check to see if this file matches the other file through calculating the MD5 sum of this file and the MD5 sum of the other file. And notice that both of the hashes are the same, which means that they are the same file. Because these are text files, you can also do a diff. And you should get no output, which indicates that the files are exactly the same. But generally, doing a hash of the files, either MD5, SHA-1, or some other hashing algorithm, is the preferred method for this. Now, I will say this is generally not the way that you will recover files. It's just a cool way to go, hey, well, we're just grabbing those sectors, popping it into a file, grabbing those other sectors, popping it into a file, combining the two files together, and it's the exact same file. So I hope that this gave you a little bit more information on how deleted files get recovered, and will give you enough information so that you can do the homeworks.